Well, hello to you, wherever you guys are. Today we're going to be talking about one of the, one of the least understood parts of AP statistics, and that's going to be transforming data to achieve linearity. Now, I'm not going to lie to you. There's going to be some mathematical background things going on here, which you may or may not be very adept at, and your however comfortable you are with it is going to, in a great way, dictate how well you do here. So, without saying a whole lot more, let's take a look at what we're doing. And here we go with transforming data to achieve linearity. So this is our into. We've got how many iPhones will be sold. Well, here's the data of all iPhone sales during their opening weekends for the years 2007 to 2015. So getting a little bit dated here, but that's okay. Data is still data. And for part one here, we're supposed to use Statlet to create a scatter plot of the data with the year as the explanatory variable and the units sold as a response variable. Then we're going to sketch that above. Well, no big deal, really. We're just going to chuck all of that into either our TI-84 or Statlet, as it says to do here, and create a scatter plot. Now, taking a look at this, I want to focus in on a couple of things, and that is here we've got years after 2000, and here we're looking at units sold in millions. And for our data, there is a distinctly curved pattern going on here. Okay, that is no longer linear. It's a really distinctive curve. So we're thinking maybe this linear data business is going to not help us as much as we think. Well, that's what we think. So would you use a linear regression to model this data? And here's what I think. A linear regression is not a good fit for the data because there is a curve in the scatter plot and there's a curve in the residual plot, which we'll look at right now. In our residual plot, we're really looking for either a U pattern or a rainbow pattern. And here in this residual plot, we see there's a U pattern that signals to us that this model is not a good fit for the data. There is a still leftover curve in the data is what some people like to say here. So, since we expect that the data is nonlinear, we can't make a linear regression. However, and this is the big however part, we can transform the data to make it more linear. Now, transform just means that we're going to use some mathematical function on either the explanatory variable or the response variable, or maybe both. Now, as it so happens, this data that we're looking at right here, I would call this exponential growth. And you've probably heard that before, exponential growth. We start off with small increases, and then the rate of increase keeps on getting bigger. So what kind of model would fit this data? Exponential growth, because the rate of increase is increasing. Now, this makes some people a little bit uncomfortable because they think there is there's some more that they need to learn in order to make that decision about using an exponential growth model. But there really isn't. If it seems like it's growing really quickly, it's an exponential growth. Now this is the mathy part of the day. What is the general formula for an exponential growth? If you're with me for calculus, or if you were with me for calculus, you probably remember the exponential growth model. It's a multiplied by x to the b. A multiplied by b to the x power. When the variable appears as the exponent, that is an exponential growth model. Algebraically, what is the inverse of this function? If we have a variable as the exponent, then we need to use a logarithm in order to unlock the exponent out of, out of the exponent, unlock the variable out of the exponent. So you're going to notice me taking a log on some of these problems. Again, this is one of the least practiced parts of mathematics, so a lot of students feel really uncomfortable here. I don't want to make you feel more uncomfortable because I really don't think it's that big of a deal. However, you should be aware of that. We can use any log we want. If you're feeling particularly sciencey, you can use a natural log if you want. Actually, that's more mathematical. Math people like to use a natural log. However, a lot of people feel really comfortable with the base 10 log, and that's okay for me. Whichever one you want to use is totally okay. So how do we transform data using this inverse? So we're going to start with that exponential model, y equals a to the bx. And then we're going to use the inverse function. We're going to take a log of both sides, and we're going to say log of y equals log of a multiplied by bx, or log of a times bx. Using properties of logarithms, we can actually separate the product by taking a log of the first factor, log a, plus the log of the second factor, log of bx. Again, this is, like I said, this is where it gets a little bit mathy, but this is one of those properties of logarithms which we are exploiting now. And now we're going to use properties of logarithms, particularly over here with the log of bx. Now, if you do see the x or anything in the exponent of a logarithm, we can actually take it out of the logarithm and just multiply by it. So another maybe unfamiliar property of logs. So now take a look at what we have. We've got log of y equals something plus something times x, which sounds to me like an exponent, like a linear model. In other words, what we're looking at is log of y equals the y-intercept plus a slope times x. Or to put it more bluntly, the y-intercept is going to be the log of a, and then the slope is going to be the log of b. And if we're interested in going back and forth between our exponential model and our linear model, then the a in the exponential model is just 10 to the power of the y-intercept. And then b in the exponential model is going to be 10 to the slope of the linear model. Don't worry, we're going to go over that all over again. So this is probably not my favorite way of memorizing this, although you're certainly welcome to memorize this part right here. I take more of an old school mathematical approach and just solve every time. So if you're like me, you can go ahead and do that as well. Okay, let's move on and take a look at our number 4. Our number 4 says we're supposed to complete the table below. And what it says to do is take a logarithm of the units sold. We're going to use log base 10. So we're going to take 0.5 and we're going to take a logarithm of that. We're going to take 1. We're going to take a logarithm of 1. What is the log of 1.7? What is the log of 4? Etc., etc. That's going to get us this table of values here. So the logarithms in blue. Some people get surprised when they see a 0 here, but yes, the log of 1 is 0. In other words, 10 to the 0 power equals 1. And of course, 10 to the first power equals 10. It's nice that we had a 10 in this chart. Use Staplet.com to create a scatter plot using the year versus the transformed data. The transformed data here is a logarithm of all of the units sold, or the logarithm of all of the response variables. Here's that data, and look at that. It looks pretty linear, doesn't it? So if you notice an exponential pattern, what you need to do is just take a log of all of the response variables, and it's going to straighten that right up. Okay, we're going to now calculate the least squares regression line for the transformed data. So again, we're going to use the year and the log of the number of units sold, and we're going to calculate the least squares regression line. We're not going to actually do that or show you how to do that. If you don't remember, make sure you refer back to the previous videos. So what we get is log of y, predicted log of y, is going to be equal to negative 1.546 plus 0.184x. Remember a couple of things here. This is not the a and b in the exponential model. You're looking at the slope and the y-intercept. So if we do 10 to the negative 1.546, we're going to get the a of the exponential model. And if we do 10 to the 0.184, we're going to get the b on the exponential model. Something like this. Okay, do you think the regression line is a good fit for the transformed data now? Why or why not? Okay, let's take a look at the residual plot. I don't see a curve in the residual plot, or maybe we should say there's no leftover curve to the residual plot. So it seems as though our transformed data looks pretty well linear. I don't know if I'd be super enthusiastic about what I write here, but I would say something like the transformed data is a better fit, maybe not the best fit, but it's a better fit, since there's no longer a curve in the scatter plot of the data, nor in the residual plot. So no curves in the data, no curves in the residual plot. That's a better fit. So, according to this model, how many iPhones should be sold in 2015? So this is the way I would actually solve for it. I would take that LSRL data, the logarithm of y equals negative 1.546 plus 0.184, and then I'd substitute x there. I'd go ahead and calculate that. The previous line calculates to 1.214. Then I would exponentiate on both sides. In other words, I would say 10 to the log y is equal to 10 to the 1.214. On the left side, since the log base 10 and 10 to the power, the exponent 10, is their inverse operations, so they, quote, cancel out, and I get that the y hat is going to be equal to 16.37, which means, according to the model, 16.37 million iPhones were sold in 2015. This is the way that I would solve this. I would do all this exponentiation stuff after I've calculated. It is a little bit easier to do it this way. So let's take a look. We're supposed to calculate and interpret the residual for the actual number of iPhones sold in 2015. So we're going to peek up to the chart, and we're going to see that over here in 2015, 13 million iPhones were sold. So to calculate the residual, we have to remember that the residual is the actual minus predicted, which, you know, the first letters there spells out wrap. So we got to wrap that, I guess. The residual, therefore, is equal to 13 minus 16.37, giving us a residual value of negative 3.37. The interpretation here is that the actual number of iPhones sold in 2015 was 3.37 less than predicted. Okay. So this takes us through just one example of using transformed data. Let's take a look at our big ideas here. And for our big ideas, we have a plot of different kinds of transformations you could do. Now, the base model that we're always going to use is this linear model where we have x versus y in our plot. However, if we think the data is exponential, then we plot x versus the logarithm of y. This is usually the one that we're going to use most often, the exponential model. So, don't worry too much about, not don't worry about it, but that is something that you should think about. The next model that we use is the power model. And in the power model, we plot log of x versus log of y. Again, any logarithmic base is going to work. In this class, we are going to use log base 10. Look at the difference between the power and the exponential model. In the exponential model, we have a constant base and the variable exponent, whereas in a power model, we have the variable base and a constant exponent. And that's the main difference between the two. Now, to make our predictions, you're going to substitute for x and you're going to solve for y. Sounds pretty normal. You may need to undo a root. You may need to undo a logarithm. This is the example that we would use here for, this is a power model. So that's how we would do it. Okay, this isn't a mathy course, so we're not going to go too heavy into these inverse operations. Let's just see what we got. You're a marine biologist interested in analyzing the lengths and the weights of Atlantic rockfish. You and your crew will be going out to catch rockfish to collect data before releasing the fish. You will be able to collect data on the length and the weight of Atlantic Ocean rockfish of several sizes. And here is a scatter plot of the data. Note the clear curved form. All right. Because length is one-dimensional and weight, like volume, is three-dimensional, a power model, A, or weight equals A times length to the third power, should be used to describe the relationship. Well, thank you very much for telling us what to do. So here is a scatter plot of weight versus the cube of length. Looks pretty linear now. Because the transformed data made in the association roughly linear, we use computer software to perform a linear regression of y equals weight versus x equals length cubed. Here is the analysis. Okay. So let's review what we just learned in the previous section. Here's my value of my value of B. Here's my value of A. Other things you're going to need to know. This is the standard deviation of the residuals. This is R squared, 0.995. And this is SEB, 0.0002. I don't think we're going to need SEB for this. This is just a analysis, not formulating our mathematical models. So let's give a equation for the least squares regression line. The way I like to see you write this is predicted weight equals 4.066 multiplied by 0.0146774 times the cube of length. Okay. Now suppose you catch an Atlantic Ocean rockfish that's 36 centimeters long. Let's use that model to predict the fish's weight. Always start by writing your equation. Substitute the length. Use the order of operations. And then just solve. Now remember that you have full access to your calculator at all times here. So really the less of the, arithmetic stuff you do, probably the better off you're going to be. So I would have no qualms about taking this equation right here, chucking that into the calculator, and just spitting out the answer like this. So that is the end here. Notice that there wasn't any really difficult solving to do. And that takes care of our first step into looking at transform data. Trust me, the AP Stats, they know that this isn't supposed to be a super mathematically intense course. So they're going to hook you up a little bit here with their requirements of the transformation of data. So that's it for us today. See you next time and have a good one.